Let us look at some of the benefits of machine learning and types of machine learning. What you see here are different pictures of dogs or fried chicken. And for us as humans, it's rather easy to distinguish them. On a few of these, you might have to have a second look, but then you won't have a problem of knowing whether it's a dog or whether it's a fried chicken. Well, what do you think? How easy is that for a computer? Well, it turns out it's rather difficult. If you think about normal, regular programming, then you would need to describe some rules how to distinguish these pictures from each other, how to know whether it's a dog or it's a fried chicken. Well, somehow both are curly, so you can't really distinguish them, and you don't really know a lot about the texture because these are only images. You could talk about the eyes a dog have. So the eyes are dark blue dots somewhere in the picture. But then looking at the fried chicken, there's some which has such dark blue dots as well. You could say, well, and there's also the nose, and the eyes and the nose are in a triangle. But then if you have three dark dots on an image, they are almost always in a triangle, except they're on a straight line. So it's really difficult to describe rules, to write down rules, how to distinguish these pictures from each other. We as humans learned it from experience. Likely you have seen none of these pictures before, but you have seen many pictures of dogs, and you have seen many dogs in real life, and you know what fried chicken looks like, and you can generalize these concepts and then apply it to these pictures and thereby discriminate between the two. But as said, it's hard to write it down in a procedural program. Now, machine learning is some kind of remedy here, because it turns out if you give these pictures with labels to a machine learning algorithm and tell it, here are a lot of pictures from fried chicken, here are a lot of pictures from dogs, and they're separate from each other, both labeled correctly, then machine learning programs can learn to distinguish these. It's not totally easy, but in general you can build such models. So with such machine learning approaches, you can resemble in some way the learning which we as humans experience, that from individual instances which we got experience and thereby improve our performance on the task of classifying these pictures. You can mimic that in a computer, and with that you can achieve performance on some problems, like this image recognition here, which would be very hard or even impossible to achieve with regular normal programming where you write down procedural rules how to process these images. And just because it's so funny, another related picture, here you see dogs or wish mobs, and it's the exact same story I had before, only that if you would talk about the eyes, then there are also dogs for which you don't see the eyes because they're hidden behind the hair and so on. So these were some examples on why machine learning might be beneficial compared to regular programming. Let's be a little more formal and consider, what does machine learning mean? And you see in the gray box at the bottom the definition from Mitchell from 1997. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. Difficult because it's rather abstract, it's difficult to remember, but let's look at the example on the top. What you see there are Chihuahuas and muffins, and it's the same story as with the images on the prior slide. For us humans, it's easy to distinguish. You might need a second look on some of these, but then you'll figure it out. For a computer, it's difficult in traditional programming. It's easier with machine learning. And this is now experience E. If you tell it, now here are 6 images. The upper left one is a muffin, then there's a Chihuahua, a muffin again, a Chihuahua, a muffin, a Chihuahua. So we have labeled training data. And the task is to distinguish, to classify between muffins and Chihuahua. Then you can provide that to an algorithm. You can ask it for a classification, and you can calculate the accuracy of these classifications. And if this accuracy on the task of distinguishing muffins from Chihuahua improves with more experience, with more training data on labeled photos on Chihuahuas and muffins, if the performance then improves, then this is machine learning. And obviously distinguishing Chihuahuas from muffins is not the real-world application which you would likely train a machine learning model on, but you can generalize this to other classification tasks or other learning tasks. And this training an algorithm with data, you provide it with experience. Here I always talk about labeled experience, so we are in supervised learning here. and then seeing that it improves its performance over time, and then later on applying this model when the performance is sufficiently good, that's a paradigm shift compared to traditional software development. This chart illustrates this paradigm shift nicely, as I think. First, let's consider classical modeling in computer programming. There you have a computer as a green box, and what do you feed in the computer? These yellow boxes? Well, on the one hand, data, and on the other hand, a handmade model. So the data could, for example, be an image for which you want to know, is it a Chihuahua or a muffin which is displayed on the image. And the handmade model could be some set of rules how to process that, looking for distinguishing features of muffins, like the paper it's wrapped in, or for the ears, nose, eyes, and so on from the dog. So you would have a handmade model and you have data, the image, you put it in the computer and it provides you a result, and for example says this is a Chihuahua, or makes a prediction on the failure of a machine in an Industry 4.0 setting, or prediction on stock prices, or whatever you try to have forecasted or predicted or classified by this model. That's a classical modeling approach. Now, what is different in machine learning? Well, again, we have a computer and we have data, but now we have sample data and expected results. This is what I meant before when I said we provided with labeled data. So the sample data are photos of dogs and wish mobs, and then the expected result is that for each of these different photos, you tell the computer, well, now this is a dog, this is a dog, this is another dog, now this is a wish mob. So these are the expected results. You provide that to the computer, and then from that it learns a model. It learns an algorithm how to classify pictures as either wish mob or dog, or whatever the task at hand is. And then you take this model and you plug it in the next round of using it. You provide new data and this learned model to a computer, and then it calculates you results on new images. I mean, for the training data, the sample data and the expected results, we already know the results. There's no real purpose in applying the algorithm to that because we already know the result. But then once the model is trained and you have this model and provide it or apply it to new images, then you get results which you didn't know before, which you didn't classify before. And now this is a big difference because in the classical modeling setting, you have this handmade model. So you know exactly, hopefully you know exactly, how the program works, what the computer is supposed to do with it. With this learned model, well, you still specify the general type of model and you still specify the learning algorithm. So in principle, you know what the model will look like and how it operates. But you don't know the inner workings, you don't know the details, and you don't know what the outcome of the learning will be exactly. So you have less control. This is beneficial in some elements because it allows you to learn models for settings where it's very hard to impossible to write them down with handmade models. So it's nice in terms of the problems we can tackle with that, but it's problematic in the sense of not fully understanding, not having the full control over what's happening in this learning process. And now with this basic introduction to what machine learning is, let's look at different types of machine learning. Well, there are primarily three different types of machine learning. The first is called supervised learning. So this is about algorithms that are trained with a lot of labeled data. That's what I've been talking about the last minutes. But there are also other types. There's also the unsupervised learning. So this is about algorithms which try to find patterns in existing data. So you don't have the labels, you only have the data, and the algorithm tries to find patterns, for example, clusters in this data. And then the third type is the reinforcement learning. This is about learning an optimal strategy for a given problem based on an incentive function. So basically there you provide the algorithm a playing field, sandbox, whatever you want to call it, an environment in which it can try out different actions, and then it observes, it gets feedback on the quality of these actions, on the outcomes resulting from that. And these outcomes might be either beneficial, then the algorithm receives a reward, or it's a detrimental bad outcome, then there's a punishment. And from that the algorithm learns which activities are good and which are not. Think about a toddler who tries to learn walking, standing up first and then walking. Likely the toddler will fall down frequently. That's the negative feedback which humans experience when they learn. But then if you make a step and then the next step and you notice that now you got it, then this is a positive feedback which leads the toddler in that example to reinforce the behavior she or he is applying for continuing to walk. So this is the analogy to human learning, which you also have in computer learning, in machine learning, here with reinforcement learning. To make the three different examples a little more concrete. Now, with supervised learning, first, as input you have labeled data. For example, you have tagged images, that's what I've been talking about, but it could as well be emails classified as spam or not, or the like. So you have labeled data, you provide it to an algorithm for supervised learning, and then the output is a classification, a prediction, a spam filter, an image recognition or so. And if you observe errors in these outputs, then you feed them back to the learning algorithm, and thereby it learns, it improves, and hopefully has less errors in the next round. That's the supervised learning. Unsupervised learning, well, there's a difference in the input. You have unlabeled data. For example, you have shopping baskets. So imagine running an online shop, an e-commerce shop, and there you have the shopping basket. You see which different products customers typically bundle together in one basket before going to the checkout. And you might want to know, does a typical shopping basket look like? Given that somebody buys beer, what else is he likely to have in his shopping basket? You might want to have that for a recommender system, for placement of advertisements or the like. This is a classical example of unsupervised learning. You have this unlabeled data, you supply it to an unsupervised learning algorithm, and the output might be a clustering, an association between different products or so on. And for example, a recommendation, which movie to watch, which different product to display on the site or so. And then if we look at reinforcement learning, then the input is a system status and evaluation criteria. For example, the distance to a target. If you want to teach a computer program or a robot how to walk, then you could give it the distance to a target as evaluation criterion and say, please walk over there. So a closer distance is good performance, a wider distance is bad performance. And again, you have an algorithm, and there are many different algorithms you could use here for reinforcement learning. And then the output is actions, for example, a running robot. And then it gets feedback, the punishment or the reward I talked about before. And this reinforces or lessens the behavior the system had, and thereby over time leads to a reinforcement learning on that occasion. I hope this gave you a first introduction on why machine learning is beneficial and different high-level types of machine learning.